Hello students. So up until last class we concluded a higher order linear differential equation with constant coefficients for both homogeneous and non-homogeneous right hand side, right? So if you have homogeneous right hand side, then we found out the solution as like finding out the solutions of this auxiliary equation, which was in terms of m, and then depending upon what kind of roots you have, we can determine the solution, right? If you have non-homogeneous right hand side, then the question of complementary as well as particular integral comes, complementary function and particular integral. So the complementary function can be determined like the analogous way we determine the solution for homogeneous equation. So you form the auxiliary equation and from there you write down the solution. However, when we are finding out the particular integral, we do that FD operator. So 1 by FD charged on the right hand side. Now depending upon what kind of right hand side you have, if you have exponential, then there is a way to find out particular integral. Within that, if fa is 0 or non-zero, I mean if you have e to the power ax, then whether fa is 0 or non-zero, based on that you can determine the particular integral. Then it can be right hand side can be of type x to the power m, or it can be of type cos x, sin x, or product of v into e to the power ax, any possible such combinations, right? So depending upon what kind of function that is given to you, you can be able to determine the particular integral. But those were all calculations that we did, those were for differential equations with constant coefficients, right? So it is how to say, relatively easy to solve them, but it may be possible that instead of having constant coefficient, you may have variable coefficients. That means our p0, p1, p2, p3 up to pn can be functions of x, and even right hand side, I mean forget about only homogeneous case, you may have non-homogeneous case. In that case also pi's will be functions of x. So then you have higher order differential equations with homogeneous or non-homogeneous right hand side and variable coefficients. So basically this lecture and probably the next lecture will devote to such problems. So let us consider a linear differential equation. So let us consider a higher order or nth order linear ordinary differential equation with variable coefficients. I think there is no dash, so coefficients. So how does that look? We will have x to the power n and x to the power n and dn by dxn plus p1 x to the power n minus 1 dn minus 1 by dxn minus 1 y plus dotted up to pny is equals to capital X, where for the time being let us mention p1, p2, p3, pn are constants, and capital X is either a constant or a function of x only, so this is called as a homogeneous linear differential equation. Now here homogeneous means different. Here this x to the power n dn by dxn, x to the power n minus 1 dxn minus 1 by dxn minus 1, it is meant in that way that it is homogeneous, right. So we are not actually saying that the right hand side is 0. So I can see the problem with the terminology, but this particular setting or this particular ODE, let us call it as 1, this is called as a homogeneous linear differential equation of nth order, right, because of this particular form, right, because of this particular structure. Now, or some people also call it, or this is also known as Euler-Cauchy type equation, Euler-Cauchy type of equation, right. Okay. So now when we are given an equation of this type, obviously since we do not have constant coefficients, we cannot simply write that auxiliary equation. So here we have to come up with a way or a workaround so that we can deal with this. So if you look at the particular form, that this is a very assuming a very specific form, you have x to the power n dn y by dxn minus dxn, then x to the power n minus 1 dn minus 1 by dxn minus 1. This will become slightly tricky if there is a mismatch in the differential order and derivative order and the power of x. So that means if you have x to the power n plus 2 and dn y by dxn, then it may not work that well, right. So then whatever method I am going to show you, you may have to do some more adjustments before you can put it into the form that I am going to show you. So first of all, let us look at this nice homogeneous structure, at this nice expression. So let us make some change in variable, right. So idea is to change the variable. So let x equals to e to the power z. So then this will imply z equals to log of x. So what will happen to dy dx? So our dy dx is basically dy dz into dz dx, because in this case we are saying we are changing from x to z, right. So there is a change in variable, and since z is a function of x, so basically what will happen is dy ds and then dz dx. So this is dy dx dy dz, and then dz dx will be 1 by x. So this implies that x into dy dx is nothing but dy dz. This is equation number 2, right. Now similarly, what will happen to second order derivative, d square y by dx square. So this will be d dx of 1 by x of dy dz. It is coming from here. So this will become 1 by x square. We will do term by term into 1 by x square into, so minus into dy dz, and then plus dy dz, 1 by x, then 1 by x into d square y by dz square, and then that will become dz dx, right. So it will become dz dx. So dz dx is again 1 by x square. So I can take 1 by x square out, and this will become d square y by dz square minus of dy dz. So as you can see, I can multiply x square on both sides by x square. So this will become x square d square y by dx square, and this will be gone. So that means x into dy dx is dy dz, then x square into d square y by dx square is d square y by dz square minus of dy dz. Likewise, you can calculate the third order derivative, expression for third order derivative with respect to x, expression for fourth order derivative with respect to x, and so on. So that means if I keep on going, then I will get all these nth order derivatives with respect to x in terms of derivatives with respect to z, and then you put all these terms back into the first equation, the first ODE with this x to the power n d n y by dxn. So, if I put all these things back, then 1 reduces to we can have d 1 reduces to, by the way, we will use d for d dx and reduces to this, and d dash for d dash d dz, sorry, not d dash but just d dz. So, we are using the short notation. So, if I use the short notation, then basically our equation will reduce to d dash into d dash minus 1 dot dot and so on, d dash minus n plus 1 plus this will become p1 d dash minus 1 dot dot up to d dash minus of n plus 2 plus dot dot and so on. This will become p n y equals to z now, because x is now changed into a function of z. So, we are denoting it by z. Now, if we look at this equation, so this is now, since pi's are constants, pi's p1, p2, p3 up to pn are constants. So, now this is a ordinary differential equation with constant coefficient in z, right. Here we do not have the equation any more valid for the variable x. Now, we have a higher order, basically nth order ordinary differential equation in variable z with constant coefficients, and of course, right hand side you have a function of z. So, that means whatever techniques we learnt in the previous chapter for constant coefficients, all those things can be implemented here, and we can solve for the variable z, right. The independent variable is z. Now, we can switch back, because we know z equals to, I think it was log x, right. So, x is equals to e to the power z, so z is log x. So, then we can replace wherever we have z in the solution by log x, and that will be the final solution, that will be the complete solution for your original equation. So, this is how this method works, right. So, all you have to do is to substitute x equals to e to the power z, and then you change the variables, and while changing the variables we will see the required ODE, that is basically to the of similar form of the higher order differential equation with constant coefficient. So, this is what we are going to do here as well by making the substitution. Okay. So, now if method is clear or the idea is clear, then we will try to find out the general solution or the complete solution of few examples. So, example 1, solve x cube y triple dash, means dy by d3y by dx3 minus x square y double dash plus 2x into y dash minus 2y is equals to x cube plus 3x, right. Let us call it as equation number 1. So, as you can see here, that nice homogeneous structure is maintained. We have x cube y triple d3y by dx3 minus x square d square y by dx square plus 2x dy dx minus of 2y, right. So, let us make that substitution. So, here x is the independent variable. So, we change the independent variable to z via z is equals to log of x, or x equals to e to the power z, or x equals to e to the power z, whatever seems convenient to you. So, obviously, x into d dx will be then d dz or z d dash basically, and similarly for d square, and similarly x square into d square over dx square and x3 into d3y by dx3, we can obtain the expressions. So the equation 1 is then reduced to d dash of d dash minus 1, d dash minus 2 minus of d dash minus 1 plus 2d dash minus of 2, 2d dash minus of 2 into of y, and then x cube will become e to the power 3z plus 3 into e to the power z, right. Okay, so we can simplify this one, and this will become d dash minus 1 whole square d dash minus 2 into y is equals to e to the power 3z plus 3 e to the power z. Let us call it as equation number 2. So now you can see this equation has now been reduced into d dash minus 1 whole square into d dash minus 2 of y equals to e to the power 3z plus 3 e to the power z. So now this is how to say, the ordinary differential equation with constant coefficients in z, right. So now we will apply the techniques that we have learnt in the previous chapter, and we will see how to solve this. So the auxiliary equation, 2 is m minus 1 whole square into m minus 2 equals to 0. So basically m is equals to 1 1 2, right. Okay, so now 1 1 2. So now the complementary function, the complementary function of 2 is yc x equals to we have 2 repeated roots, right. So it will be c1, one root is repeated twice. So one repeated root, right, not 2 repeated root, one repeated root. So c1 plus c2z into e to the power lambda z, so e to the power z plus c3 e to the power 2z. So this is the required complementary function. Okay, now the particular, let us call it as equation number 3. Okay, equation number 3. So the particular integral is given by so this is not x, this is z, sorry, and we will have ypz is equals to 1 by fd, that means 1 by d dash minus 1 whole square into d dash minus 2 e to the power 3z plus z plus 3 e to the power z, 3 e to the power z, right. So at least we have this part up to this part. Now we will again do this distributive thing. So we will have 1 by d dash minus 1 whole square d dash minus 2 e to the power 3z plus 3 1 by d dash minus 1 whole square d dash minus 2 into 3 e to the power z, right. So 3 e to the power z, yes. So now we will substitute d is equals to a. So in the first fraction it is not becoming 0, whereas in the second fraction it is becoming 0. So we will substitute d is equals to a, so e to the power 3z. So we will have 2 square into 1, and here we will have 1 by so we will take 3 into e to the power z, 1 by I am substituting d equals to d plus a. So, this will become 1 minus 2 and 1 by 1, let us go 1 by 1 and 1 by d dash minus 1 whole square e to the power z. Okay. So, the first fraction will become 1 by 4 e to the power 3z minus 3 1 by d dash, let me see what do we have. So, d dash minus 1 whole square. So, this will become d dash minus 1 whole square e to the power z, right. So, now this will be 1 by 4 e to the power 3z minus of 3 e to the power minus of e to the power z and d dash minus 1 d dash plus 1, sorry, d 1 by d dash plus 1 minus 1 whole square. So, this will be 1 by 4 e to the power 3z minus of 3 e to the power z 1 by d dash square of x square of z square, sorry, d dash square of 1. No, so this is d dash square of 1, right. So, that means we are integrating twice, right. So, this will become 1 by 4 e to the power 3z minus 3 e to the power z of z square by 2. That means we did the integration twice. So, z square by 2. So, this is the required particular integral. So, hence the required particular integral somehow this pen is sort of stucking, I do not know. Hence the particular integral is yp 1 by 4 e to the power 3z minus 3 e to the power z square by 2. So, the required the complete solution is y is equals to yc plus yp, and if we go to yc, sorry, so yc is what was it? I think it was c1 plus c2z into e to the power z plus c1 plus c2z plus into e to the power z plus c3 e to the power 3z e to the power z 3 c3 e to the power 2z plus whatever we had 1 by 4 e to the power 3z minus of 3 e to the power z, what was it, z square by 2, z square by 2. So, this is the required complete solution. Now, we will go back to x. So, this is c1 plus c2 into log x plus c3 e to the power 2z, that is e to the power 2 log x plus 1 by 4 log of e to the power x equals to e to the power z. So, z equals to log x. So, this will be 1 by 4 3 e to the power log x minus 3 e to the power log x into z is log x. So, log x whole square by 2, if I have done correctly. So, then in that case this will become c1 plus c2 into log x plus c3 e to the power. So, basically this will become c3 x square plus this will become c3 x square plus 1 by 4 x cube minus 3 by 2 x log x whole square, right. So, this is the required complete solution that we were looking for our non-homogeneous PD or non, in the sense homogeneous PD, but not exactly the right hand side 0. So, we had I mean sort of like x cube d squared d3y by dx cube plus x squared d square y by dx square and so on. So, when we are given an ordinary differential equation of that type, that means this special homogeneous type. So, then we substitute x equals to e to the power z, and from there we try to reduce the equation or derive at an equation where we had how to say this x3 into d3y by dx cube, all those things will get cancelled, some terms will get cancelled, some terms will get adjusted here and there, and ultimately the differential equation that we will obtain, that will be basically in terms of z. So, there you have dependent variable as y, but independent variable is taken as to be z, right. And then we have this ordinary differential equation with constant coefficient, for which the methods have already been learnt, and then we substitute this equation by we calculate the complementary function and particular integral via the same method, and then we substitute back into the solution, and where we have yc plus yp, that is this equation as you can see, and then we use z equals to log x, right. So, the working principle is not difficult. The working principle is still the same, that if you have a constant coefficient equation, then you can get complementary function and particular integral. It is just that from your original equation where you have this homogeneous setting x3 d3y by dx cube, how do we come to here? So, that is what we are basically concerned with. So, we have a this substitution x equals to e to the power z, which actually serves the purpose. Like this there can be many examples, and most of the examples are just you take x equals to e to the power z, reduce it, then solve it, then again reduce it back to the original solution setting, right. So, I believe here we do not need to solve a lot of examples here, pretty much it is straightforward. So, I will just write one more example just for your own convenience. So, solve x square into d square plus 3xd plus 1 into y equals to 1 by 1 minus x square 1 minus x whole square. So, the solution is you again substitute x equals to e to the power z, so that the given differential equation will reduce to d dash plus 1 whole square into y of y is equals to 1 by 1 minus e to the power z whole square, right. So, here d dash is basically our d dz. So, if you do those magical calculations, then it will reduce to d dash square d dash plus 1 whole square of y equals to 1 by 1 minus e to the power z whole square. So, from here the complementary function will be c1 plus c2z e to the power minus c2z e to the power minus e to the power plus, not minus. So, of course, so there is a plus. So, yeah, definitely e to the power minus of z. So, that is complementary function, and for particular integral we have to treat it like 1 by d dash plus 1 whole square of 1 minus ez whole square. So, from here we just have to go term by term. So, you expand 1 minus e to the power z using our usual square formula, and then we distribute it term by term, and we see what if it is d equals to a, making it 0 or not. If it is not, then we do it in that way. If it is 0, then there is another method. So, like this there can be many examples in this chapter, but most of them are applicable from x equals to e to the power z point of view. We just make that substitution, reduce it into the differential equation with constant coefficient, and then we write down the solution by calculating complementary function and particular integral, right. So, this chapter is just similar to the ones with diffusion not diffusion reaction, but this differential equation. So, second order ordinary differential equation. It's just that here you have this variable coefficient, in the sense you have x to the power n, x to the power n minus 1 and so on. there you had constant coefficient, right. So that's the only difference, but the working principle is more or less same. It's just that you are using the substitution x equals to e to the power z, right. So I believe rest of the examples you'll get from the assignment sheets, and you can practice and solve and get good at it as much as possible. And in the next class we may try to solve few more examples, or we'll start a new chapter.